Hello students, welcome back to your class on virtual memory. In the last class we saw about your page replacement algorithm. So we saw to the various algorithms, that is your first in first out, optimal page replacement algorithm, and your least frequently used page replacement algorithm. When we addressed to each of the algorithm, we saw the problems that is associated, and we saw how to actually use the reference string, and when there is a number of frames that vary, what could be the number of page faults. We also saw to the advantages and disadvantages. Now, so among the three algorithms, FIFO gave us a large number of page faults, and if I say optimal algorithm gave us very less page faults, but probably it was not practically implementable because of the disadvantages it had, that is predicting the future pages. So LRU was better than your FIFO and had page faults lesser than your FIFO. So now let us see some of the implementations that we could make to your LRU, because that was one of the practical approaches we had which gave us less page faults when compared to your FIFO. Now let us see how we could be implementing your LRU. So one of the two implementations is your counter and the other one is using your stack. Now what happens when I am using a counter? Each page table entry will have time of use field. Let me just get it down. So here in the counter we use a field time of use field and add to the CPU's logical clock or counter. The clock is incremented for each memory reference, and when a reference to the page is made, the content of the clock register are copied to this time of use field in the page table entry. So what happens? In this way we get the last time the page was referenced. So by this we are able to see if the page is recently used or not. So if we have a very low time, that means that it is not eligible. If we have a very low time, probably that is a page that is eligible to be replaced. If it has a very high time, then it is the page that is recently used and shall not be replaced. So this is one of the ways by using the counter where we could be implementing your LRU. The other one that we have is using your stack. So what do we do using your stack? So we maintain the recently referenced page on the top of the stack. So whenever a page is used, that page shall be put on the top of the stack. The top of the stack will always contain the most recently used, and the bottom of the stack will contain the least recently used pages. Then how do we implement it practically? Probably here the stack will be implemented using your doubly linked list, which will have a head and a tail pointer. So what happens if I say the head is assigned to be the top of the stack? So every time the recently used page will be on the head, and if I say the tail is assigned with the bottom of the stack, so the tail will have the least recently used. So the page that can be replaced, it can be at the pointer tail, and the page that is recently used will be at the head. Now we can see a small illustration here of the page 2 and 7. If 2 was recently used, so that is on the top of the stack, and next I have 7 that is recently used. 2 is pushed down, and then I have 7 on the top of the stack. And you can see 4 here. If I just look back, 4 is least recently used, that is 4 is not referenced for a very long time. So this is another method how we could be implementing LRU. And you may be thinking why the implementation of LRU is considered and not the FIFO. As I told it to you earlier, optimal page replacement is not practically possible, and FIFO suffers with a major disadvantage, that is your Bilady's anomaly. So both of it is not something that is preferable. So having said that, LRU is something that is preferable, and that is the prime reason where we are seeing to various implementation techniques of your LRU. The other thing that we have is other approximations of your LRU algorithm. That is, what are the other ways that we could approach it? The other technique is to use the reference bit. So what happens here? Each page is associated with a reference bit. So many systems provide the reference bit for every entry in the page table, which is set any time by the page when it is accessed. Initially, all the reference bit in the page table will be set to 0, and then whenever a page is referenced, it will be set to 1. And this reference bit can be cleared periodically. So what will happen by this reference bit is, we can distinguish from the page that has been accessed since the last clear and from the one that has not been accessed. Now if I say I clear the reference bit, or I set everything to 0 for every 2 minutes, or say let me say for every 5 minutes, so I get to know after that I have cleared which is the page that is referenced and which is not referenced. So if the reference bit is 0, then I can treat that as the victim page, or the page that is eligible to be replaced. If the reference bit is set to 1, then that indicates that the page is recently referenced and it cannot be replaced. A small variation to the reference bit. Here we are talking about having a single bit. So it can only take two values. Either it can take a 0 or a 1. So I told here, so this reference bit is periodically cleared. Now rather than setting the period, I am using an additional set of reference bit. Rather than 1 bit, I am dedicating 8 bits or 1 byte. So this will give me a history of 8 instances of time. So if the reference is made for the first time, second time, third time, fourth time, fifth time, up to 8 is where I am able to get the information of whether it is accessed or not accessed using this 8 8 additional reference bits. Here also, what do we always consider is the one which has the lower value will always be the victim page. Now let us see how it works. So what happens here is, on a regular time interval there will occur an interrupt and the control will be transferred to the operating system. Now what will the operating system do? It is going to shift the reference bit for each page into the higher order of 8 bits, shifting the other bits to right by 1 and discarding this lower bit. As it shifts, it would be discarding the lower bit. By this, any point of time I refer to this shift register, I get the history of 8 instances of time. Now if I say the shift register is reading this value, then probably this page is never referenced and it is eligible to be replaced. Now if I consider the counterpart, if I say it is 11111, probably the page is referenced every instance of time and it is not eligible to be replaced. Or if I consider these two, so if I just take up to the decimal values, this value is 196 and this has a value of 119. So you can see here, this is the page that is used more recently than this page. You can see this page values higher than this page. So the page that is not most recently used, or the shift register value which is low, will be the one that is eligible for replacement. The next algorithm that we have is your second chance page replacement algorithm. Now what is about the second chance page replacement algorithm? Let us get back to the reference bit algorithm that we were talking about. So what is that we told? There will be one reference bit that is associated to each page. Now if it is 0, it indicates the page is not referenced and it is eligible to be replaced. If it is a 1, so if a bit value is set to 1, it indicates that it is recently referenced. So what happens in your second chance? Because it is recently referenced, it is going to give it a second chance. So when it sees a 1, it is going to clear that value and it is going to set to 0. And after that, it is going to visit other pages in circular fashion and find if there is any other page that is eligible to be replaced, or if it is getting a victim page. Now, so when the second time, when the operating system comes for the second time, and if the page still remains to be 0, it indicates that after it is cleared the value, the page is not replaced and it is eligible to be replaced. Now meanwhile, while it is parsing to these pages and it is coming back to it, meanwhile if there is a reference made again, this reference bit will be set to 1 and again it is the operating system, the algorithm is going to set it to 0. So this happens until it gets eligible to be replaced. So having spoke about your second chance place replacement algorithm, so here we are using the reference bit. A small modification to the same is where we will be using the reference bit with the modify bit as well. If you remember, last class we spoke about your technique of page replacement, where it is going to check with this modify bit or the reference or modify bit or the dirty bit. So the combination of the reference bit and modified bit will be used in your enhanced second chance algorithm. So what happens here, you can see I can have 4 different combinations of this. That is, if it is 0 0, it is neither recently used nor modified. If it is 0 1, it is not recently used but it is modified. If it is 1 0, it is recently used but it is clean. This could be a case of a read-only page. It is accessed but there is no modification that is done. And the last one is it is recently used and also it is modified. Now what happens here? We saw the second chance algorithm works in the circular fashion here. So in the first parse or the first time, it is going to check for the page that has 0 0, that is neither recently used nor modified. Now if it is not finding a page with 0 0, for the second pass it will try to find a page with 0 1, not recently used but modified. So that is how it is going to work with the pass. The main difference with the second chance and the enhanced second chance is the preference for replacing a clean page is possible. So this is about your some of the implementations that we looked in with your LRU. The last set of algorithms that we have is your LFU and MFU algorithms. So why is this called a counting algorithm is where we could be implementing it with the use of the counter. So LFU is least frequently used and MFU is most frequently used. So the title itself tells. So the page that is least frequently used will be the page that is eligible to be replaced. Whereas in MFU it is totally opposite. So the page that is most frequently used will be the page that will be replaced. Here it is based on an assumption that because it is most frequently used, it may not be called again. So both of it, as I told, can be implementing using your counter. Here, apart from the reference, there is another value that we take, that is the frequency with your counter. So every time it is referenced, the counter value keeps incrementing. That gives us the frequency of how many times it is being referenced. So based on that, the page replacement happens. So this was about your page replacement algorithm, and we addressed to some of the implementation techniques of your page replacement algorithm. We saw that pages was something that was addressed to your logical address space, and frames was something that was your physical address space. Now, as a user or the CPU could see to the logical address space or your page. Now, for that page to be executed, it must try to fit in itself into a frame. Now what is this about the frame allocation? Now if I say I have a main memory and that main memory is divided into frames, let me say I have around 50 frames in my main memory. Now this 50 frames, which process, how many frames do I allocate? Should I be allocating all the process the equal share of frames, or is there any technique that I could be deciding? Now for any process to execute, we should allocate some minimum number of frames. Now if we do not allocate, if the number of frames that we have allocated is too less, then again it is going to have a page fault, and again it would waste most of the time in faulting and again getting the page and all of it. So how is this frames decided to a process, that how many frames should be allocated to a particular process? We have two techniques. One is fixed allocation and the other one is proportional allocation. Now what is fixed allocation? Now if I say I have 20 frames, I shall be giving 10 frames to each of the process, allowing 5 process to be executing, or 5 process that I can be having in the main memory, which would increase my degree of multiprogramming. Or let me say it would something be like I have 2 where I'm giving 25 to each process. So basically fixed allocation is dividing the main memory into your fixed number of frames. Now proportional allocation has something to do with the process size. Now if I have 3 processes, let me say process P1, P2 and P3. Now process P1 is of size, let me say 1 MB, process P2 is of size 5 MB and process P3 is of size 10 MB. Fine. So what happens in fixed allocation? I am allocating the same amount of frames to all of it. So process 1 also gets 10 frames, process 2 also gets 10 frames, process 3 also gets 10 frames. Whereas in your proportional allocation, depending on the size of the process, I vary the allocation of the frames. That is, I could say that process 1 gets 10 frames, process 2 gets 20 frames and process 3 gets 30 frames. So it will not fit into, okay, let me just reframe it. Process 1 gets 5 frames, process 2 gets 10 frames and process 3 gets 20 frames. So what am I trying to depict here is, in proportional allocation, depending on the size of the process, the allocation of the frames shall be decided. Now, having spoken about the frame allocation, the next thing that we have is about your local or global allocation. That is, whenever the page needs to be replaced, it could be done locally or globally. That is, if I am allocated 10 frames to a process and it is requiring a page replacement, I replace it among those 10 frames only. If process P1 is allocated 10 frames, the replacement will happen among those 10 frames. That is your local replacement. So the number of pages allocated to a particular process is fixed and the replacement occurs only among those pages that is allocated to a process. But that is not the case in case of your global. If I say the main memory has 50 frames, it could select its replacement from any of those 50 frames. Any page may be a potential victim, whether it is currently belongs to that process or it is seeking a free frame from another process. So that is about your global replacement. So local replacement always allow a process to better control their own page fault rate and also lead more consistent performance of a given process. The next thing that we have is one of your issues with the replacement, that is thrashing. Now what is thrashing? Thrashing is a condition where the system is spending major portion of its time in page faults, but the actual processing done is very negligible. If I have to put it in a nutshell, a process is spending more time paging than execution. When does this situation of thrashing occur? Now, if I say there is a process that does not have enough frames, that is, the number of frames allocated to a process is very low, what happens? It will quickly have a page fault. During this, it must replace some page that is not currently in use. So, subsequently, it will again fault because there is a replacement of the page that is happening. Now, when I replace the page, that page is removed out of the main memory and put it into the secondary storage, because if I am having it, if I again need the page, then again it is going to fault. So what is happening here? The process is spending too much of time in paging rather than execution. So the process continues to fault, replace the page, again it faults, again it replaces the page. So high paging activity is your thrashing. So what could be the causes here? One of the major cause is to increase the degree of multi-programming. Now we can see the graph here. At a particular point, you can see there is a drastic drop that happens. So why is this drastic drop that is happening? Now, if the CPU is idle because we are spending most of the time paging, so the operating system thinks that it is necessary to increase the degree of multi-programming, and it is going to add another process with a very few frames. So what happens again? So again that will also start faulting. So the CPU utilization is triggering a chain reaction of high page faults. So that will immediately start thrashing. That is, you can notice here, I am trying to increase the degree of multi-programming. The CPU utilization is good. At some point, the CPU utilization drops very badly because the CPU spends most of its time where there is swapping happening and the CPU is not very effectively used. And the other cause that could be there for the thrashing would be the global page replacement as well, where it is borrowing the pages from the other process and the other process also starts thrashing, so no process would have completed its execution. Now, what are the ways that we could be avoiding thrashing? So here there are two methods that could help us to avoid thrashing. One is the use of local replacement. As I told, global replacement is one of the causes. So we could avoid using global replacement and we could use local replacement. So by doing that, what happens if one process starts to thrash, it cannot steal the frames from another process. So that will be only one process that would be suffering. But in the other case, it could also have other process involved in thrashing. The other solution that we have is the locality model. Now, what is a locality model? It is a set of pages that are actively used. The locality model states that as the process executes, it moves from one locality to another. A program in general is composed of several different localities which may overlap. For example, when a function is called, it defines a new locality where memory references, and then each of its function calls, local variables, global variables, all of it has a different locality of memory reference. So that is where, so now we try to have an understanding of what is a locality model. So based on this locality model, we have the working set model, which is a technique to handle thrashing. So what does the model tell? Now, if we allocate enough frames to a process to accommodate its current locality, it will only fault whenever it moves to a new locality. But if the allocated frames are lesser in size than the current locality, definitely there are chances to thrash. So according to this model, we use the value delta, so that is the working set size. Now, if the working set size is too small, it may not comprise the complete, even an entire locality, that is, even a single locality could not be covered. If the size of the delta is too large, it may have many localities in it and it may lead to overlapping. So it is very important to choose the right size of delta. Even if it is too small, it is an issue. If it is too large, it is overlapping. So it is necessary to have an ideal size of delta. Then we define working set size of a process I that contains the total number of pages that is referenced in the most recent. Now you can just take a glimpse of it here. So if I say this is the delta, that this is the working set window. So in this working set window, so the pages that are referred are 1, 2, 5, 6, 7, and another reference, that if I say this is my working set window delta, then the pages that I have referenced here is 3 and 4. Now what does the model tell? If I define D to be the total demand for pages, then it would give up to the summation of the working set size of a process I. So it tells to make sure that if I consider M to be the number of frames that is available in memory, so if the demand is greater than the number of pages available, definitely it is going to thrash. So it is always better to suspend that particular process. That is, I repeat, if M here is the number of frames that is available in the memory, if the number of frames is greater than the demand, then definitely it is going to thrash and it is better to suspend one of the process. We should always see that demand is less than or equal to M, which is the number of frames that is available. If there are enough extra frames, then some more process can be loaded in the memory. So in summation of working set size exceeds the availability of the frame, then some process have to be suspended. So that is about your working set model. So this technique prevents thrashing and it also ensures some good degree of multi-programming. So it also ensures that CPU is well utilized. The last technique that we have is the page fault frequency scheme. So this is another approach that we have to handle thrashing. So as discussed earlier, what was the issue with thrashing is it had a high page fault rate. Thus, we need to control the page fault rate. If the page fault rate is high, it indicates that the process has too few frames allocated to it, and if the page fault rate is low, it indicates that there are too many frames allocated to a process. That is where we fix up a upper bound and lower bound for the desired page fault rate. If the page fault rate falls below the lower bound, then the frames can be removed from that process, and similarly, if a page fault rate exceeds the upper bound, then the number of frames can be, more number of frames could be allocated. So it is always ideal to remain in this particular region. So here if the page fault rate is high with no free frames, then some process can be suspended and the frames allocated to them can be reallocated to another process. The suspended process can later be brought back to the main memory. So these are some of the ways how we could be avoiding thrashing. So as told, thrashing is doing nothing useful other than just swapping. So it is very important to handle thrashing, else we may have a severe performance issues. So this is about your virtual memory, students. Thank you.